Hi there, welcome to my channel. My name is Prabjot Kaur. In today's video, we are going to learn about two of the commonly used activation functions in neural networks called Sigmoid and Softmax activation functions. I'm sure at some point you may have wondered whether there is any relationship between these two functions and what's the math behind these. So let's explore all of that in this video. Before we study about the sigmoid and the softmax functions, we need to know what is an activation function in the context of neural networks. And also for the classification, there are two possible problems. There's more than two, but the two commonly used classification problems are binary classification, where you have only two possible outcomes, and then you have multi-class classification, where we can have more than two classes as outputs. So now that we have a little bit of a background, let's get into the details. We'll start with a sigmoid function, since we have already learned about this when we studied about the logistic regression in one of the previous videos. So you already know what this is, but just to briefly go over the details, let me repeat some of the important points. So the sigmoid activation function is used for binary classification. So the core of the sigmoid function is this function right here. It's called logistic function. So it's basically it's a function that says 1 over 1 plus e to the power negative y. So it takes a scalar. So y is a scalar, and it converts that number into a probability. So this y bar is a number between 0 and 1. So it's a probability. So it takes any scalar and converts that into a probability, which is a number between 0 and 1. And what that number is, it's actually the probability of predicting the positive class. Since there are only two classes for the binary classification problem, so we know that if we know the probability of class 1, the probability of class 0 or class 2 would just be 1 minus probability of class 1. So let's take a look at what a neural network might look like that is using sigmoid function in the final layer. So here we take just one input sample, just let's say it's one image, and you want to classify that image, object in that image, into maybe, let's say, whether the image contains a dog or a cat. So there are only two possible classes. So then we pass that image into a neural network. Here I am only showing two layers, but you could have many hidden layers. So let's say this is one of the layers, and then in the final layer we will have just one neuron which takes the input from the other neurons, and we know that the base for the fully connected neural networks, this is the basic equation. So the output of this neuron is going to be the weighted sum of inputs from the previous neurons. So let's say the output is negative 3.0 in this case. But for the output layer, we cannot just output this as the final output. We pass it through a activation function, and in this case we use a sigmoid function, and this sigmoid function converts this number into a probability. And the way it does is using this formula right here. And this is the probability of predicting class 1, and then the probability of predicting class 0 is simply 1 minus this number. So simple. Sigmoid function is pretty much this formula. So now let's move on to the softmax function. So the softmax function is used for multi-class classification. So as we saw in the previous slide, the sigmoid function takes a scalar and it converts that number into a probability, which is the probability of probability of class 1. In the softmax, we want to know, because we have more than two possible classes. So you can have, in this example, let's say I can have 4 possible outputs. So I give it one input, let's say one image, and then I have 4 possible outputs, whether the image contains a dog, a cat, a rat, or a fruit. I'm just making these numbers, making these categories up. So we have 4 possible outputs. So what Softmax does is it also converts the outputs of the neural network, the final layer of the neural network, into probabilities. However, the key difference here is, first of all, the mathematical formula used for softmax function looks like this. So what this formula is, so let's say the output layer contains, in this case, very important to know, in this case, the output layer it should have 4 neurons, because we have 4 possible outputs. And each of those neurons is going to do this calculation, which is weighted sum of the inputs of the previous neurons. And each of this is going to give us a number. Then we pass that vector into our softmax activation function, and it gives us also the probabilities, just like we saw in the previous slide. So the key difference here is, firstly, the number of neurons in the final layer when we use the softmax function must equal the number of outputs, in this case 4. And then we take that vector and pass that through the softmax activation function, and what we get is a set of probabilities that correspond to each of those outputs. And the important thing is the sum of all of these probabilities must equal 1. So the output, the way we interpret the output is, when we give it an input sample, then there are 4 possible outputs. And based on the output of the neurons, when it converts that into a probability, the way it reads is, it has 0.0048 probability of predicting class 1. It has 0.791 probability of predicting class 2, so forth and so on. So the predictability is distributed amongst 4 classes, and then usually we say whichever is the highest probability is the final class. So that's how we read the output of the softmax function for the multi-class classification. But now let's look at the mathematical formula for the softmax function. So here it's actually pretty simple. So it takes in the vector, so it will take this vector, and z is the vector, all of this, and then we take the exponent of each of the numbers here. And the reason why we take the exponent is because we want to convert all of these numbers to positive numbers. So that's the first thing we do. So we take the exponent of each of these numbers, and then we normalize. When we say we normalize, we simply take the summation of the exponents of all of these numbers, meaning the exponents of the input vector. And that's really what the softmax function is. So pretty simple. Now, you may be wondering if there is any relationship between the sigmoid and the softmax function, and the answer is yes. Actually, the sigmoid function is a special case of the softmax function when we have binary classification problem. And if you want to dive deeper into understanding that relationship, I would encourage you to check out these 2 references here. These are the only 2 references that I found when I was reading online what the relationship is between the 2, and these 2 references are really good, especially the first one. It goes into full math of how we can derive the sigmoid function from a softmax function. So I encourage you to read through these if you are interested in learning more. Now we are ready to code. So let's get started. Okay, let's define our softmax function. We will create a function in Python. Let's call it softmax func, and it takes in a vector. So I'll just call it vector z, and then we calculate the probabilities using the formula that we saw before. So P equals it's basically we take the exponent of the vector and then we divide that by the summation of the exponents of all the elements in that vector. So np dot sum of np dot exponent vector z, and then we simply return the result. Yep. So let's on this, and let's say this is our input vector, -3, 2.1. You can pick any numbers, but I just simply chose these set of numbers in the z vectors that has both positives and negatives and even 0. So, and then I am going to call the softmax function on this input vector. So let's call it p softmax equals softmax function z, and then maybe we want to print p softmax. Okay, let's see what we get. Okay, how can we make sure that our answer is correct? So the simplest way to do that is we can simply see what is the summation of all of these probabilities. So if I print the sum, it should equal 1. So let's see if that's the case. np dot sum of p softmax. And it is, I mean, it's not exactly 1 because we're dealing with the floating points. So the answer is correct. And then you can even try giving other numbers. Let's say, let's give it 10. So now let's try to see what the answer is. So again, the final answer is 1. And as you can see, 10 has the highest probability, 0.999, because 10 is the biggest number. So just very simple calculations basically. Now, just for comparison, I'm also going to define the sigmoid function. So let's just define the sigmoid function, and it takes a scalar, so I'll just call it z, and we'll say p equals 1 over 1 plus exponent of -z, and then I return p. Okay, now let's again call our sigmoid function on the same vector. So we'll say sigmoid func z, and then we will print p sigmoid, and we will try to check what the end result is. Like, so in this case, say we should not be getting sum of probabilities is 1, and I'll explain in a little bit. Let me just finish up the code here. So we want to do np dot sum of p sigmoid. Okay, so let's see what we get. See, all right. So now let's go through what I just did. So the first thing is very clear. So we defined a softmax function, and we know softmax function can takes in a vector, and then we got the result, and this is the vector of probabilities that correspond to the input vector z, and then the softmax function, the sum of all the probabilities must equal 1, and then we check that it is equal to 1. Okay, so we are clear with the softmax function. Now, just for comparison, I wanted to see what result I get if I pass this vector into a sigmoid function. Now, you may be confused or asking, why am I passing a vector to the sigmoid function? So in reality, for the sigmoid, all you need is a scalar. So in this case, for the softmax, this is one input. So let's say I have an image just like I showed in the slide, and that image has four possible outputs, or in this case 1, 2, 3, 4, 5, five possible outputs. So then for that single image, for that single input, I have this vector that I'm passing through the softmax function, and these probabilities are probabilities for each of the possible classes. However, for the sigmoid, when we saw the slides, it only needs a scalar. So let's say I have a single image, and then in the single image, you can have two possible outputs, cat or a dog. So then the final layer only has one neuron. So it's actually a single neuron. So in this case, the reason why when I pass vector, it does not mean I'm passing one input. Here, each of these inputs that are in the z vector, each would correspond to a different input sample. So please don't get confused like why I used z as a vector input to the sigmoid. It's actually not, it's not representing a single input sample for sigmoid. It's actually representing 1, 2, 3, 4, 5 input samples. So that's the key difference. But what I wanted to show here is if we pass that z vector into the sigmoid function, then the results are different, of course, because we are using different mathematical formula, and the summation does not have to be equal to 1, and because these inputs are actually not related, they don't belong to one single input sample. So that was what I wanted to show today, and I hope this was helpful. And if you ever get confused again between softmax and sigmoid function, come back to the video, and hopefully this might provide a little bit of a refresher of what it is. With that, I will end the video here, and if you love the content on this channel, please consider subscribing. I would love to have you as part of my channel. With that, thank you, and I will see you in the next video. Bye.